Reinforcement learning is the most prominent techniques to train AI models till now, especially on simulated tasks. We have seen LLMs are getting trained with GRPO, PPO. Let's go back in time and learn about the ancestor of modern RL algorithms, which is Q-learning, which was originally introduced in the 1992 paper. This single paper laid the foundation from the Atari games to the fine-tune of AI assistant like ChatGPT. As you know, in RL, you have an environment, an agent who takes action and get reported by the environment. Imagine the agent is standing in the state and wondering, if I take this action, will it going to be valuable? Will it going to be really good? That answer is given by Q values. It's the agent's best guess of the total reward it can earn by taking action A in state S. To train an agent to perform the best in an environment, we define all the Q values of all the actions with its state. So let's suppose there is 4x4 grid world and an agent can take action up, down, left and right. Taking the action left from state 0 will lead to the agent to hit the wall, which is a bad action. Therefore, the Q value of the action left from state 0 should be lower, maybe negative, compared to taking an action right from the state 0. Now initially, we don't know the Q values. That's why we learn it through trial and error process. We define the table of Q values of action corresponding to each state, which is also called Q tables. In our world, we have 4 actions and 16 state. We will have like a total of 64 Q values. We start with zeros in the Q tables. When the agent reaches to the goal, it will get +1 reward and there will be no intermediate reward. So in between states, there will be 0 reward. And if it gets hit by the wall, it will get like a -1 penalty reward. An agent can take actions until it completes an episode. In RL, an episode represents one complete run. It starts from the initial state, takes action step by step, and ends either after reaching the goal or a number of fixed steps. After each episode, the agent resets itself, try to attempt the same goal again. Okay, that's great, but how the agent will going to learn these Q values? We want the agent taking the best action in a state S should have the high value and bad action in a state S should have the low value. So in inference, when the agent taking an action, it can just like do the max of Q values and can identify which is the best action. During each episode, it gathers experience consisting of actions, reward. These experience forms a trajectory which stores in a replay buffer. But in our example, which is very, very simple, so we don't need like a replay buffer kind of thing. After every episode, we compute the return, which is the sum of all the rewards collected during the episode. So G is basically R1 plus R2 plus R3 plus R4 and then till the Rn. Rn is basically the total steps it took in an episode. It treats the reward at step 4 as same as step 100. To make the agent value earlier rewards more than later ones, we need to introduce some kind of a discount factor. The discounted return G is defined as GT equals to RT plus gamma RT plus 1 and then gamma will be like at power 2 RT plus 2. This method of calculating the return is called Monte Carlo method. In classical Q-learning, we don't wait until the end of an episode to update our estimate. Instead, after every step, the agent updates the Q value of the current state action pair using the temporal difference rule. What exactly the YT is here? YT is basically the R plus T1, which is the future of the reward, plus gamma max of QST plus 1, where A prime is all possible action that the agent could take from the next state, ST plus 1. So if the YT is greater than the current estimates, it means the action turned out better than expected. So the agent will increase its Q value on that state. And if the YT is lower in this error, the outcome is worse than the expected. So instead of Monte Carlo method to compute the returns, we can just use temporal difference. And here we arrive at the Bellman equation, originally introduced in 1957, which is just a function which takes S and the action value. This equation means that we update the value of taking action A and state S based on how good the resulting outcome is compared to the previous estimate. In deep Q networks, or basically deep Q learning, where we use a neural network to approximate Q functions, we store experience in the replay buffer and sample mini batches to stabilize training. but in our environment is very simple grid world. So we don't need a replay buffer or wait for full episode return. We can just update the queue values after every step using the temporal difference update rule. I have built a simulation which you should try it out. I can leave the link in the description. You can see initially all the queue values in the table is 0, and when we take a step which is based on sometimes random for acceleration or deterministic action which is based on max of queue value. So if we increase the value of epsilon, you can see the agent makes more random moves, and if we decrease it to 0, the agent is deterministic and take only the best action. So this was all about the queue learning. I hope you liked the video and enjoyed it too. So